You ever stop and wonder why some things happen in the blink of an eye, while others seem to take forever? Well, today we're pulling back the curtain on the hidden world that controls the pace of, well, everything. We're talking chemical kinetics, the science of speed.
So let's kick things off with a question. How is it that a pressure cooker can whip up a meal in minutes, but an iron nail left outside might take literally years to rust away? I mean, it's the same planet, same laws of nature, so what gives? The secret, it turns out, is all about mastering the speed of chemical reactions.
And that's exactly what we're about to get into. We're going to uncover the fundamental rules that dictate the speed of every single chemical change, from the food on your plate to the fuel in a rocket ship. At the very heart of all this is a field called chemical kinetics. And put simply, it's the rule book for how fast things happen in chemistry. It's not just about if something will react, but how fast it's going to go. It's all about understanding, and this is the cool part, learning how to control that pace of change. Okay, so if we can figure out what controls the rate, we can basically become masters of these reactions, right? Think of it like a control panel with all these different dials we can turn to either speed things up or, slow them way down. Let's take a look at the most important dials on that panel. First up is concentration. Picture a nearly empty room versus a sold-out concert. In that packed concert, people are constantly bumping into each other, right? Well, it's the exact same idea with molecules. When you have a high concentration, you've just got more molecules jammed into the same space. That means more collisions, and more collisions mean a faster reaction. Simple as that. All right, next dial, temperature. Cranking up the heat is basically like giving every single molecule a double shot of espresso. They just start zipping around with way more energy. So not only do they collide more often, but when they do collide, it's with a lot more force. That makes it way more likely that a reaction will actually happen. This is exactly why we cook our food. We are deliberately speeding up chemical reactions to make it tasty. Of course, there are a few other factors in play. The physical state makes a huge difference. Gas molecules are flying free, so they react way faster than liquids or solids. Having more surface area helps too. Think about how fast powdered sugar dissolves compared to a solid cube. But the real game changers, the MVPs of reaction speed, are catalysts. These things are like chemical superpowers, and we'll circle back to them in a bit. So we know the big things that can change a reaction's speed. But for a scientist, just knowing what changes the speed isn't quite enough. They want to predict exactly how much it'll change. And for that, they need the secret recipe. This brings us to what's called the rate law. It's the tool that lets chemists predict reaction speeds with incredible precision. Now, the rate law is a mathematical equation, but don't let that term throw you. It's an incredibly powerful concept. It takes us beyond just saying more stuff makes it go faster. No. It gives you the exact relationship. It tells you precisely how much faster things will get, connecting the amount of your ingredients, your reactants, directly to the reaction's speed. Okay, let's try to wrap our heads around this with a quick puzzle. Imagine you're running a reaction. You double the amount of one of your ingredients, let's call it reactant A, and all of a sudden, the whole process is happening 4 times faster. So what's really going on there? Let's break it down. First, we observe what happened. Doubling our ingredient quadrupled the speed. Then we find the relationship. The change in the rate, 4 times, is the square of the change in concentration, which was 2 times. 2 squared is 4. See? And that relationship tells a chemist that the reaction is second order for A. It's just a precise way of saying the rate depends on the concentration of A squared. And just like that, the rate law helps us solve the puzzle. But wait, there's another piece to this whole puzzle. We talked about all those molecules bumping into each other. So why doesn't every single collision cause a reaction? The answer lies in something every reaction has to conquer, an energy barrier. This barrier has a name, activation energy. The best way to think about it is like trying to push a huge boulder up a steep hill. It takes a ton of effort, a lot of energy, just to get it to the top. But once you do, it can just roll right down the other side with no problem. Well, chemical reactions need that same initial push of energy to get over the hill and get going. And this chart here shows that idea perfectly. You've got your reactants just sitting there at their starting energy level. They need a big boost of energy to get all the way up and over that activation energy peak. Only the molecules that make it over the top can actually transform into products, which are often sitting at a lower, more stable energy level. It's all about that initial climb. So how do we make that climb easier? Remember those catalysts we mentioned? This is where they work their magic. A catalyst doesn't get rid of the mountain, but it does something even smarter. It builds a tunnel straight through it.
It provides a shortcut, a whole new path with a much lower activation energy. This means way more molecules have enough energy to make the journey, and the reaction speeds up, sometimes by millions of times.
Okay, so let's bring this all home and see how this stuff actually shows up in our world. Because understanding all these principles isn't just some abstract science experiment. It has literally shaped the modern world in some really profound ways. 200 million. What do you think that number is? That is the number of metric tons of ammonia produced every single year. It's made possible by something called the Haber-Bosch process, which uses a catalyst to speed up a reaction that would otherwise be impossibly slow. And that ammonia, it's the main ingredient in the fertilizer that helps feed billions of people around the globe.
And what about this one? 2 to 3 times. Well, by simply lowering the temperature in your refrigerator, you are using kinetics to slow down the chemical reactions that make food spoil. This super simple application can make our food last 2 to 3 times longer. That's less waste, more food, and money saved. So yeah, why does this matter to you? Because it is literally everywhere. It's in the medicine you take, designed to react at just the right speed in your body. It's in the safety plans that prevent explosions at chemical plants. It's in our fight for the environment as we create catalysts to break down pollutants faster. It is even in the battery of the device you're watching this on right now.
Which brings us to a final thought. We've learned how to engineer one of the most fundamental forces in the universe, the speed of change. We can essentially control chemical time. So the big question is, what's next? What's the next great global challenge we can solve with this power? The possibilities are incredible. The only question is, where do we start?